This lecture is a continuation of our discussion on free body diagrams. Please review STO4 and STO5 for background information. In the context of static equilibrium of rigid bodies, given a system like this tractor, we are often interested in determining one or more unknown forces that are either internal or external to the rigid body. By external forces, we mean applied loads and support reactions. By contrast, internal forces are those found inside the system. For example, here, the reaction forces that the ground exerts on the tractor are considered external to the system, whereas the force in, say, cylinder R, or the forces that develop inside link X, are considered internal. But why the interest in these forces? Because we need to know them in order to be able to properly design the system. We need to make sure the system can withstand the internal forces that develop during its operation. To determine a force or a group of forces, we should start by drawing a relevant free body diagram. For example, to determine the force in cylinder R, the free body diagram must show the force in the cylinder. To expose the force, we need to cut the cylinder like this, and then continue cutting until we isolate a part of the system. In this process, any time that we cut through a part of the system, we need to show the internal forces at the cut point. In this case, we can cut close to the pin in order to isolate the shovel. We know the pin transmits two forces, a force in the X direction and a force in the Y direction. We can consider the shovel as a rigid body subsystem for which the equilibrium equations must be satisfied. The free body diagram of this subsystem involves four forces: the force in the cylinder, the two forces at the pin, and the weight of the shovel, which is placed at its center of gravity. Assuming the weight is known, we have a total of 3 unknown forces here. If we know the relevant distances, we can easily compute the force in the cylinder by writing and solving the equilibrium equations. We'll come back to this step a bit later. For now, let's keep our focus on the process of drawing free body diagrams. How do we determine the force in cylinder M? We start by cutting the member, then continue drawing a curve in order to create a closed loop that isolates a part of the system. Here, the best way to create the loop is to cut close to pin B, like this. By doing so, we expose the two forces at the pin. There is also the weight of the shovel and that of the arm. We label the former W1 and the latter W2, both of which are known forces. In this free body diagram, we have 3 unknown forces, which can be easily determined by writing and solving the equilibrium equations. What if we wanted to determine the force in cylinder L? What would the free body diagram look like? Again, we cut through the cylinder and then cut at the pin. We can close the loop by having the entire arm as our isolated subsystem. For this case, we add the weight of the upper arm to the free body diagram. And if we want to determine the internal forces acting on link Y, we have to isolate it from the rest of the system. To do so, we can cut here, 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 and here. These 4 cuts enable us to isolate the link this way. Our free body diagram then can be drawn like this. There is a force in each cylinder, and each pin has 2 forces associated with it. The weight of the link, W2, is a known force. This free body diagram has too many unknowns to be determined using the equilibrium equations. There are 6 unknown forces and only 3 equilibrium equations. We need to calculate 3 of them using another free body diagram before we can use this one to determine the rest. For example, first we can use this, the previously drawn free body diagram, to determine these 3 forces. Then we can write the equilibrium equations for the link, and solve them for the 3 remaining unknowns. We can determine the internal forces in link X in a similar manner. We isolate the link and draw its free body diagram. Here, too, we have too many unknown forces. So we need to use another free body diagram to calculate 3 of the unknowns. Previously, we drew this free body diagram for calculating the force in cylinder M. Given that the diagram has 3 of the unknown forces, we can use it to calculate them. The remaining 3 unknowns can then be determined by writing and solving the equilibrium equations for the link. In summary, to determine specific internal forces in a rigid body, we need to isolate a part of the body that exposes the forces. But if more than 3 forces are exposed, since we can only write 3 equilibrium equations per free body diagram, we would need to look to other parts of the system for additional relevant equilibrium equations. Let's actually calculate a few of the internal forces for a specific arm position. Suppose we are interested in determining the force in cylinders R and M, and the internal forces at pins A and B in link Y. The free body diagram for the link looks like this. Since there are more than 3 unknown forces here, we need another free body diagram, another set of equilibrium equations, to be able to find all 6 unknowns. Let's use the free body diagram for the shovel. It shows 3 unknown forces only, so we can solve for them using the equilibrium equations. They are solving the last equation for FR, we get, then from the second equation we get AY, and the first equation gives us AX. Let's update the free body diagram for the link by substituting the computed values for variables FR, AX, and AY. Now we can easily calculate the remaining 3 unknowns using the equilibrium equations for the link. But to write the equations, we need angle beta. It equals 42.71 degrees. Then the equilibrium equations become solving the last equation for FM, we can determine BX using the first equation and BY using the second equation. Now we know the internal forces at the joints of link Y. We will continue this conversation in the next lecture.